Okay, so let us start the session now. Uh, so in the last session on Saturday, I have discussed the concepts of weak 8, projection on a vector and projection on a vector space, and projection on an orthonormal basis, and how to get a orthonormal basis using Gram-Schmidt process, and what is orthogonal transformation. So today's session is on week 9. So should I start from week 9, or do you want to solve some questions from week 8? So just raise your hand who want to do week 8 questions today. And
Excuse me, Atul.
yes.
I just have a question, not regarding week 9 or week 8 per se.
Hmm.
Quiz 2 mocks have been released. I think we got a mail today. So just wanted to clarify if you will be having a session maybe next week going over the mock questions.
Okay. So
Is that scheduled?
so quiz is on next Sunday, right?
Next Sunday, right? Tomorrow Sunday
Yes.
and then the
Yeah.
Sunday after that.
So we on Saturday we can discuss mock solution.
All right, all right, all right. Thank you. Yeah.
Okay. Yeah. So who have completed week 8? Raise your hand. Completed in the sense solve the assignment, graded assignment. Okay, just quickly unmute yourself and just tell me whether I should solve the questions for week 8, or should I discuss week 9 today. Just everyone one by one tell their opinion. Nobody is raising hand or not telling.
Sir, actually, the quiz 2 is up to week 8, right?
Okay, yeah. So for
So, if it is helpful to discuss about it week 8.
yeah, I now understood. So everyone is focusing on quiz. So week 8 is good actually. So okay, so let's solve some questions. Okay, and I'll give you some time to solve the question, and then I'll discuss. Okay, this way we'll do. So let's start from solve with us. Okay, then we'll solve practice assignment as well. Okay, so first point is so this concept will be used in this question one. Okay, one, two, or maybe, yeah, one or two questions. Obtaining orthonormal set from an orthogonal set. Okay, so everyone solve this first question, or if you want to read this key point one, just read this first and then solve the first question number one, which is asking which of the following subset of S consist of mutually orthogonal vectors. So just you have to check which one are the orthogonal. Okay. Okay, so in this question, this was simple, so that's why I am solving early. Uh, you have anyone who has doubt in this question number one? So in this question, it is asked which of the vectors are orthogonal. So because it is given in the question, the inner product is simple dot product. So and orthogonal vectors are which when the inner product is zero. Okay, so you just have to take the dot product of each of the vectors and see whether they are that is zero or not. Okay, so all the combination of two vectors, if we take the dot product between them, we'll get zero. Okay, anyone who has doubt in this question number one?
No, sir.
Okay, uh, just ask. Okay, if anyone has any doubt, just ask. You have to ask, otherwise I'll just move on to the next question. That's why everyone solve this question number two. Let's take 5 minutes. So we are solve with us question number two. Okay, week 8. You can open your on your laptop as well. Okay, if I'm not sharing screen. Okay, so any doubt in question number two? Anyone who has not able to solve?
Sir, can you just verify option 5?
Option 5,
Yes, sir.
our last option, is an orthonormal basis. So first we will check whether the every vector has norm 1. So first one is, first one is 2 1 1 and root 6, so it is 4 1 6, yeah, it is one norm. Second is also, third one is also, so it is norm 1. We just have to check whether they are perpendicular. Okay, so we'll take dot product between the first two. Then, so what will be the dot product? Root 2 2 by root 18 plus, okay, so then minus 1 by root 18 and minus 1 by root 18, so that means minus 2 by root 18. So yes, so first two are actually perpendicular, and you can check the last two, for which 1 by root 6 and plus, yeah, this is also perpendicular. And first and last, for first and last, you, yeah, this is also perpendicular. Yes, they are orthonormal. This is orthonormal basis. Okay.
Okay, sir.
Everyone, solve this question. Question number 3. Okay.
Excuse me, sir.
Yes.
Sir, there's a deadline coming in week 6 practice assignment due to which I'm unable to access the answers. So, do you have any PDF or something of the practice assignment of week 6?
Yes, sir. It is. Has it not been shared yet in the supplementary content? No.
No, sir.
Oh, I think the solutions are on this, I guess. Oh, let me see. Okay. Link to the recorded live session. Sources. Maybe in the resources. Okay, questions. Okay, practice questions, not practice assignment. This is one playlist PA videos solution. So these are all the practice assignment solutions. Okay.
Okay, sir. And sir, I have a doubt in week 6. I have posted it in the discourse and tagged you. Can you please give that answer after this class?
Okay.
Okay, sir.
Today are you posted or
So I posted yesterday, then I today edited it and tagged you again.
okay? Where is your question?
Hello, sir.
Hmm.
Sir, the graded solutions and the practice solutions, where it is available, sir, for Max 2?
I think it is actually shared with you uh, in your dashboard, but this time I'm not sure why they are not sharing. So I will ask ma'am. Okay, after this session, I'll ask ma'am to share.
It's not available anywhere, sir. That's why I'm asking.
Okay, I will ask ma'am to share the solutions for the graded assignment as well. Okay.
Okay, thank you, sir.
Okay, so everyone solved this question number three, or any doubt in this? Okay, so who has solved this question? Raise your hand. Who have solved? Just raise your hand using clicking on this icon of hand. This question number three of solve with us. Who have solved and mark the answer? Please raise your hand. Okay, so I'm giving you more time. If you at least one of you have should be solved, then I will discuss. Okay. Okay, so meanwhile, you guys are solving that question. I'm okay. After that, I will discuss it. So now, if anyone solved, just raise your hand. That question, this one. Solve with us 8, question number 3. Who have solved? Raise your hand. You can click on this right hand, on this raise hand icon. I'm assuming nobody has solved. Okay, so just take more time. Okay, okay. Pratibhi, can you tell me how did you solve this? I mean, in this question, which it is asked that you have one vector, okay, and you have to find out the projection of this vector on the subspace. Okay, so these are the orthonormal bases.
Sir, I have taken the like value of u is given.
Hmm.
So for spanning, I have taken the value of v1 and v2. Like I have the first vector I play, a vector is a v1 and second is v2. Then use the formula of projecting v1 v2 on u equal to u dot v1 whole v1 plus u dot v2 whole v2, and just put down the values and calculate them.
Okay, I'm solving for rest of you. If this is the question, and you have to find the projection of this vector u on this. Okay, so the first vector is this, and second vector is this. So how to find the projection on the subspace? We just project on the basis vectors of that subspace, because we are already given the orthonormal basis. We just so when the bases are orthonormal, what is the projection on the first vector? Suppose of this. So suppose that projection is p uh, on w. Okay, of u. This is given as projection of this one, first one, and projection of the second one. So the first one projection is, I will take the inner product, okay, of this u, which is given here, with this 1 by root 2 comma 0 1 by root 2. Okay. With this vector we'll take the inner product uh, with this, okay, and then we will multiply by this vector. Okay, suppose I have taken okay, just write the whole vector, like 2 comma 0 by, okay, just take the inner product and multiply with this vector. This is the projection. This formula is correct or not for projecting on the first vector. Similarly, projecting on the second vector is, you take the inner product with this 1 by 3 2 by 3, okay, and multiply with this vector on which we have finding the projection. Okay, so everyone is fine with this statement. Prithvi, you also in this way you did, right?
Yes, sir.
Yes. So suppose if it is not a orthonormal basis, then which additional step we would be adding here? If it is not the orthonormal basis, I mean the norm is not one for the vectors. Then we will be dividing by the norm. Okay. So norm is square. Where is the formula? Is there any formula? Formula is not given, but we will be dividing by the norm square of that vector. Okay, on which we are finding the projection. But because it's the orthonormal basis, so we don't have to do this. So now everyone solve it, okay, and just take some more time, okay. And inner product is just the dot product, okay. It is given, I guess. Inner product space, then the projection of this. Yeah, this is usual inner product, okay. That means dot product. Okay, all of you just solve this expression that I have written. Okay, now raise your hand who have got the answer. One Pratibhe, you did that. Okay, rest of them, anyone? Okay, Abhijit, you got the answer. So let us solve this now, because I am not sure whether you are got the answer or not. I mean, rest of you guys, because you are not raising your hand. So because we have already the expression, we have to just put the values. So first, so we take the inner product or the dot product of this u with the first vector. So it will be like 2 upon root 2, 2 upon root 2 plus it is 0, and then minus 2 upon root 2. Basically, so it will be 0, right? So inner product is 0. So 0 times anything is 0. So first one is 0. Second one, use this, and we'll take the dot product with this minus 2 by 3, 1 by 3, 2 by 3. Okay, so dot product would be minus 4 by 3. Okay, and plus 1 by 3 and minus 4 by 3, right? So this is the dot product, okay, and we are multiplying with this vector, okay. What is the dot product? We solve out. It would be minus 8 by 3 plus 1, so minus 8, that is 7. So minus 7 by 3 times this vector, minus 2 by 3 comma 1 by 3, 2 by 3. So okay, so now I think you will be able to solve from here, right? Which option is true?
Sir, first one.
Yeah, first one. And now just to make sure that you guys are able to hear all of me, who have understood this question solution, all of you raise your hand who have understood the solution. Okay, Neha understood. Rest of you, Abhijit, you also raise your hand, even if you solved. Just I want to see whether you guys are responsive. Why you are not responsive? I'm not audible or what? All of you raise your hand. Okay. Still, these guys are not raising their hand. Okay. So you guys are not understood. Then please, any one of you unmute and just tell me whether
Yes, sir, understood, sir.
actually these guys are not raising their hand, because I think there are 13 people in this meet, and raised hand are only four. Okay, I don't know why. Okay, I'm just moving on. Okay, whoever doubt, just unmute and ask. Okay, no problem.
Sure, sir.
Okay, question number three. Question number four. All of you solve this question number four. I'm just now I'll go quickly, because now I know that you guys are not raising your hand anyway. Okay, I'm just ask you just one or two guys that whether you have understood or not, you have doubt or not, and I will move on. Okay.
Okay, sir.
Yeah. All of you take 5 minutes and solve this question number four. Okay, so who have solved this question number, this question, raise your hand.
Yes, sir, just solving.
Okay, solving, but have you find uh, this basis for this? How to find the basis?
Yes, sir, just there is
Yes, sir.
some inner conflict.
Okay, okay.
Yes, sir. I find
Yeah,
out.
yeah. I will be. I will discuss at 8:40. Okay, no problem.
Okay, sir.
So in order to find the basis, we have to express it in a parametric form.
Sorry, can you repeat?
I said in order to find the basis, we just express it this equation x minus y plus z equal to 0 in a parametric form. So I can have assumed, let's say, y equal to some kind of say, s, z equal to t. So then we can express
Oh,
these three numbers.
actually, there are three variables x, y, and z. So
Yeah,
clearly, two variables would be independent, right?
correct. So we need it's going to be
So yeah, so
x,
we
y.
can replace two variables by anything, right? Suppose x and y, we have taken 1 0. Okay,
Right.
then z would be 1, right? So 1 0 1, this is a 1 point on this, and the other point is suppose 0 1. uh, okay, 0 1 minus 1, right? So these are 2 points. Now you just make them norm 1 by dividing their norm. Now you will get a two vectors which are independent. Okay, and which are independent, and so but they are not orthonormal. Okay, remember. So for orthonormal,
Yeah, that is the Gram-Schmidt curve. So first, before even normalizing, I got 110 and then minus 101. I think if those are correct. I mean, I think when
uh,
I take
which one you got? Which one? Can you tell me
one
again?
one 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 zero
Okay,
and then minus 101.
okay. So you just multiply both of them. Zero. Yeah. So clearly, these are perpendicular, and now because they are satisfying as well, minus one, uh, 0, and okay, not minus 1. Okay, this is not satisfying this. I think it should be
0,
0,
1, 1.
0 minus 1 1. Oh, okay, okay. Minus 1 0 1, right? So minus 1 0, and this would be 1. Yeah, this is also satisfying. Minus 1 0 1. This is satisfying. Okay.
So that's what I have to.
Yeah. So these are two vectors. These are two vectors which are perpendicular. Okay. Now you just have to divide by their norm. Okay.
Yep, square root of 2. Yeah.
Yeah.
So,
So now because you
Sir,
have the, yeah,
so we
yes.
can call the first one as
sir,
1 and the second one
zero
as
one one is one vector.
0 1 1.
Yeah, 0 1 1 and minus 1 0 1 or 1 0 minus 1.
Yeah,
These two are basis vectors.
this is also on this plane. Okay, no problem. We just have to check whether they are perpendicular as well or not. So they are not perpendicular. These are not perpendicular. Okay. So because now you have to these two vectors, your task is very simple. You just project on this first vector. So similar way, you just take the dot product. So I'm just directly taking the dot product with this. So which is 1 0 0. So 1 by root 2, I guess, first one, and multiply by 1 0 1 0 1. Okay, plus this is a projection on the this first basis. Okay, on second basis, this is minus 1. So this is minus 1 by root 2 and 1 by root 2. So it is 0, right? Only this one. This is only 0. This is the projection. Okay, and projection is given. This is ABC, and what is asked is 3 times A plus B plus C. So 3 times A plus B plus. Okay, I think we have done some mistake. Oh, okay. Okay. Anyways, we are just finding first the solution. A and B and C. So A is 1 by root 2 and C is also 1 by root 2 and B is 0. Okay. So 1 by root 2, 1 by root 2 is 2 by root 2, that is root 2 times 3. Yes, 3 root 2 is the answer, but I don't think this is correct answer.
Yes, sir, basis vector is 0 1 1.
Which one? I mean, these are not bases, you are saying, telling, right?
The basis vectors of the subspace I'm talking about.
What are the basis vector? These are basis vector, right?
110 is not the basis vector. No.
One
I
one
got
zero
0, 1, 1.
1 minus 1 0. This is on this plane, right? What is the problem? And minus 1 0 1 minus 1 0 and 1. This is also 0, right? So both the
Yeah.
two vectors are on this plane, and they are perpendicular, because when you take the dot product, you'll get minus 1 0. Oh, sorry, dot product is not 0. They are not perpendicular. Okay, they are not perpendicular vectors. That's why we are getting the wrong answer. These are bases clearly, but this is not orthonormal basis. Orthonormal basis means they should be perpendicular and the unit vector one. So they are not perpendicular. Whoever told this, they are not perpendicular. So for this, I will just remove this.
So this is where I can do. I can start with these 2 points satisfy, but then I can give the first one, and I can use Gram-Schmidt to rotate the second one to make it
Yeah, yeah,
orthogonal to the first
yeah,
one, right?
yeah. That's what we will do. That's what we will do actually. So I can just take the first vector, which is uh, 110, right? So we will just divide by its norm 110. Let me check again. Yeah, yeah, this is set one. So this is the first vector W1. Okay, norm 1 and uh, and uh, and on this plane. Okay, so and how to get W2, the second vector, perpendicular vector? We will take any vector, okay, which is on this plane. So suppose, can you tell me any vector on this plane? Anyone?
0, 1, 1,
0 1 1.
1.
Okay, let me check. 0 minus 1. Yeah, this is on this plane. So this is just simple vector. We don't care whether this is perpendicular or not. We'll just subtract the projection of this vector on the first vector. Okay. So projection would be take the dot product times this vector. Okay. So dot product is 1, right? Sorry. What is the dot product? 1 by root 2, right?
Yeah, 1/2.
1 by root 2 the dot product times this vector, okay, this vector itself, so which is 1 by root 2 times this. So 1 by root 2 times 1 by root 2 is 2. Okay, 1 1 0. So this is the projection of this vector on this, and we are subtracting this. Okay, now this we get the W2. Okay, so this is 1 by 2. So 1 by 2, 1 by 2, and we'll subtract this 1 by 2 from this, so we'll get 0 minus 1 by 2, that is minus 1 by 2. Okay, comma 1 minus 1 by 2, which is 1 by 2, and 1 minus 0, which is 1. Okay, so we can remove this 0. Minus 1 by 2, minus 1, plus 1 by 2, and 1. And we will divide this by its norm, and norm of this vector is 1 by 4 plus 1 by 4 plus 1. This is 2 by 1 by 2 plus 4, 3 by 2. So when we divide by this vector, it will become root, root 2.
2/3.
Okay, 2 by root 3 under root. Okay, so this is the perpendicular, this is the second vector. Okay, now we will calculate. Can you simplify this somehow? Okay, no need to simplify, just directly project. Okay, this vector 101. So 101 on first is when we project 101. Okay, this is the vector 101. So project on the first vector, we will get 1 by root 2, and only 1 by root 2. Okay, but the dot product one, 1 by root 2 times this again 1 1 0. This is the projection of first vector, and projection on this W2 we'll calculating now. Okay, So which is, take the dot product with this, and this would be minus, okay, whatever it is, okay, let me put it, 2 by 3 under root, and minus 1 by 2 is multiplied here, minus 1 by 2, this is, plus this second vector is 0 and third one is plus 2 by 3 times 1, right, this one. So when we subtract, we will get 1 by 2, 2 by 3 times 1, uh, the dot product and this entire vector, which is 2 by 3 minus 1 by 2, 1 by 2, 1. Okay, so this one. So when we multiply, we will get 1 by 2 times 1, 1, 0 plus 1 by 2 times 2 by 3 minus 1 by 2, 1 by 2 and 1. So here 2 to cancel out, we will get 1 by 3. Okay, so 1 by 2 minus 1 by 6, this is one vector. Okay, second vector would be 1 by 2 plus 1 by 6 comma 1. Okay, so this would be 3 3 minus 1, that is 2 by 6, that is 1 by 3, and this is 4 by 6, that is 2 by 3 comma 1. Okay, so this is the projection vector. This is A, this is B, this is C. So when we add them, we will get 3 by 3. Okay, sorry, 3 by 3 plus 1, which is 2. So this is the value of A plus B plus C. Okay, and what he asked, 3 times of this, so which is 6. 6 is the answer. Everyone got this? How to
Yes,
do?
sir.
Yeah. This question number 4, right? Now, now we solve the one question on Gram-Schmidt process. I think in this question, we are not needed to use Gram-Schmidt, but we have to use to find the perpendicular vectors. Okay, so I'll see whether I have some sort of method or not. Okay. Meanwhile, you guys solve the question number 5. Okay, where we have one vector and then find the value of root 3 times ABC. And what is this? Question is given here. Let beta be an ordered basis for the inner product space R3 with the usual inner product, and beta is this, gamma is this, be the corresponding orthonormal basis obtained using Gram-Schmidt process. Okay, so gamma is the orthonormal basis, okay, which is made from this beta. Okay, so what you have to do is you just take this beta and convert into gamma. Okay, all the vectors in the orthonormal basis. When you get it, then you will get this answer. Okay, question number 5, 6, 7. So all of you, I'm just giving you more time to solve this 5, 6 and 7. Okay. Okay, so should I discuss now or more time?
Yes, Ayuma.
Okay, so uh, uh, I'm not solving this question. If anyone want me to solve, then I will solve only. Okay, because if you have solved, then there is no need to solve. So anyone who is not able to get, just tell me. Okay, so I'm just solving. Okay, just one more question. I'm solving on Gram-Schmidt process. Okay. So how do we solve this? We take the first vector. Okay, we'll call it v1, 1 1 minus 1, and we will divide this v1 by root 3, its norm. Okay, and then we get w1. So we have converted this v1 into, so basically these vectors are v1, v2, v3, and we are converting into w1, w2, and w3. Okay, so w1 we will get 1 by root 3, 1 1 minus 1. Okay, simply. And v2 is 1 1 0. Okay, and then I will take the projection. Okay, of this vector on w1. So what is the projection? And then we will subtract that. So 1 1 0 minus, so projection would be when we multiply these two vectors, take the dot product of these two vectors, we'll get okay, where so this 1 by root 3 plus 1 by root 3 minus 1 by root 3. Okay, so these two cancels, only 1 by root 3. So 1 by root 3 is dot product, and vector, what was the vector? Vector was 1 by root 3 times 1 1 minus 1. Okay, this is the vector. So what we will get? What we will get here is 1 by 1 minus 1 by 3. Okay, which is 2 by 3, comma 1 minus again 1 by 3, that is 2 by 3, and 0 minus 1 by sorry, this would be this is minus 1 by 3, so it would be plus 1 by 3. Okay, so this is v2, and now to get w2, I will divide this vector by its norm. Okay. What will be the norm of this vector? So 1 by 3 comma 2 2 1, and this has 4 plus 4 plus 1, that is 9. Okay, so when we divide by 9, that is under root 9, that is 3. Okay, and for this 3 we will multiply by 3. So basically this vector is already, I think, unit vector, right? Can you see this? Norm of this vector is already 1. Okay, so this vector is simply just 1 by 3 2 2 1. Okay, this is already unit vector. So we get w2 and w1. Similarly for w3, we take v3 and subtract the projection of on w2 of this v3, and minus projection on W okay, W1 first and then W2. Okay, so this is W2, this is W1. You just take the projection of this vector V3, okay, and subtract. You'll get W3. Not W3. You'll get some vector, suppose x3. Then when x3 divided by its norm, then you will get W3. Okay, so this is how you will get these three vectors. Once you get these vector, then there is nothing because these vectors are here, so you can actually find the value of a b1 to c1 and calculate this. Now all of you solve the. So anyone any doubt in these questions? How to get? Okay. Solve this question number 8. 8 and 9 both question are solved, and then we will discuss together. Okay. Concept is simple: orthogonal transformation. Okay, orthogonal transformation means the inner product of the vectors, and after taking the image or the image in under T, then take the inner product. Inner product should be same. Okay, then we can say that projection, that transformation is orthogonal. Okay, and orthogonal matrix follow this property: A into A transpose equal to A transpose A, and both are equal to the identity matrix. Okay, these two are the properties. On the basis of this, solve these two question 8 and 9. I'll discuss after 5 minutes. Okay, so who asked this question on discourse? Is that uh, is he here? Ask that question on discourse. This one. Name is Vardhika.
No, sir, C isn't here.
Okay. Anyway, but if for solving this, okay, let me answer this. Option one. Okay. Um, yeah. Has anyone solved the question that I gave you? This one, question number 8 and 9. So whoever has solved, raise your hand. Solving. Okay. Yeah. Okay. Take some more time. Okay, so to solve this question, I'm audible.
Yes, sir.
Okay, so to solve this question, how do we have to check whether the inner product is same. Okay, so suppose x and x y this. So if you take two vectors in R2, suppose x1 x2 and y1 y2. These are two vectors we are taking. Then if we take the dot product should be not this one. I'm taking x1 y1 and x2 y2. Okay, then we take the dot product. Dot product would be x1 x2 plus y1 y2. Okay, this is the dot product. Let's check whether when we take the image of these vectors and then take the dot product is same or not. Okay, for t1 we are checking. So image vectors of x1 y1 would be x1 plus y1 by root 2 comma x1 minus y1 divided by 2. This is the first vector. Take the dot product with second vector. Second vector would be x2 plus y2 divided by root 2 comma x2 minus y2 divided by 2. Okay, so when we take the dot product, we'll get x1 plus y1 divided by root 2. When you multiply, it will be 2, right? Times x2 plus y2, comma second vector would be x1 minus y1 x2 minus y2 divided by 2. Okay, and plus. Okay, this is the dot product of these two, the image vectors. Okay, when we add them, so before that we will just multiply, so we will get x1 x2 plus x1 y2 plus y1 x2 plus y1 y2 divided by 2 plus, so 2 is same, so we can actually write the entire 2, and we can write this also x1 x2 plus plus y1 y2 and minus y1 x2 minus x1 y2. So x1 y2 and x1 y2 cancel out, y1 x2 and y1 x2 cancel out, so we'll get 2 times this, so this would be equals to 2 times, so these two terms would be added and divided by 2, so we'll get x1 x2 plus y1 y2. This is same as this because the inner product is same. So this first one is t1 is orthogonal transformation, right? Similarly you can check for others. Yeah, take some time to understand this. Now take some more time and solve for others as well, and tell me whether you are getting the correct answer. Um, Now, should we move on to the next question? Okay, so next one is this orthogonal matrix. So for that, so suppose,
Solved, sir.
okay. So for this one, I'm just solving for first for whether this is orthogonal or not. So for that, I will just take this matrix 1 0 0 minus 1, and I'll take the transpose of this 1 0 0 minus 1. So this is a transpose of this matrix, and I'm calculating the product. So product would be 1 and 0 0. Okay, so this is identity matrix. Yes, so this is true. Similarly, check for other. Uh, Now we have solved this entire exercise. Should we solve practice assignment? I mean, before solving, I'm just want to ask you. You guys haven't solved this practice assignment for week 8, right? Anyone who have solved already solved? You, Abhijit, you are already solved.
Yes, sir.
Okay, and what about others? Okay, so let's discuss that. Okay, so all of you solve the question number 1, which is inner product is given, and match a set S in the column A with a set T given in column B, so that T is uh, the subset of span of S pulp, and match the set in column B with the property it satisfies in column C. And dot product, inner product is defined as the standard dot product. Okay. So can you tell me how to find the span of S perp? Anyone? Oh, this is information is also given. Suppose W1 W2 is vector space, and W1 plus W2 is uh, vector in W1, and W2, just add those vectors, and then we'll get W1 plus W2. Okay. One can verify that W1 plus W2 is a subspace of V. Okay, this is given, this property. If there are two subspaces, then the summation of these two subspaces are also a subspace. Okay. So yes, can anyone tell me how to find the span of S perp?
So slightly confusion. So can you help it with
For in what? In which
the
question?
same question,
This
sir? Yes, sir.
how to find the span of S perp, right?
Yes, sir.
Okay. So span of S means simply suppose this option A, it has only one vector. Okay, and three questions are all have only one option, and in D there are two vectors. So span of all the combination span you already know. So span of this vector space, and we'll that will be a vector space, right? And we have to find a vector space. I mean a set of vectors which are perpendicular to that vector. Okay. So we will find the one perpendicular vector to this vector, okay, and then all the multiples of that vectors is in the span as per, okay. So this is one way. Suppose I'm explaining the first option. Okay. I'm explaining the first option. So first option, this is one vector minus 2 1 3, okay, and then we have to just find the perpendicular vector. So take any vector which is perpendicular to this vector. Can you tell me one vector which is perpendicular? So I'm writing this minus 2 1 3 minus 2 1 3. This is one vector, and dot product is the standard dot product. So you have to just tell one more vector so that the dot product is 0. So let's try to guess one vector, and here suppose 1 comma 1 2, whether this is perpendicular to this minus 4 plus 1 plus 3. Yes, this is 0. So dot product is 0. So these two vectors are perpendicular, right? So uh, these two vectors are perpendicular. So basically, uh, because this is perpendicular vector, so all the multiples of this vector will be the perpendicular vector to this. Okay, 2 1 1. Okay. So 2 1, or we can find the unit vector. That would be good actually. So it would be good if we choose the vector, the random vector from the given sets. Suppose let's check the first option, 0 1 1. 0 1 1 is not perpendicular to this minus 2 1 3. Okay. Second option, uh, 1 minus 1 1. This is 1 2 and minus 2. The first vector is perpendicular, and 2 1 1 is perpendicular. Oh, sorry, I'm checking with the second one. First one is minus 2 minus 1 and 3. Yes. So the second set, clearly the second set is mapped to A to 2 here. This option. Okay.
Yes,
Let's
sir.
quickly check. Okay. So similarly you can and then further column C is saying first option saying forms an orthonormal basis of a vector space which is isomorphic to R2. No, because there are two vectors, but perpendicular to one vector is enough. Okay. Okay, it's just saying for R2. Okay. For R2 we'll need two vectors. Okay. For R2 we need two vectors. So let's check whether, yeah, because they are perpendicular together. So 1 1 1 1 0 and 2 are not perpendicular. These two vectors are not perpendicular, but they are independent. So they will form the basis, but not orthonormal basis. Okay, so that's why the second option is not mapped to one. Let's check the second one. Orthogonal, but not orthonormal, not orthogonal even. They are not perpendicular, not orthogonal. Yes, so third option could be true. Let's fourth option, orthogonal but does not form the basis of a vector space which is isomorphic to R2. So uh, but it is saying orthonormal, okay, which is not. So third option is true for this. A 2 3, A 2 3. Yes, this is true. Okay. Okay, take some time to solve. This is a big question, so I'm giving you
Yes.
10 minutes to check for all the options. Okay, for all the property, and if you have any doubt, you can discuss. 9:45. We'll discuss this. So do we move on to the next question, or
Yes, sir.
anyone want to ask any question in this? Question number one. No. Okay. I guess if anyone want to ask, you can ask. Otherwise, solve this question number two. Okay, this we will discuss quickly because you can take some time, but it would be difficult for you, I guess. Okay, but still you can check.
Okay, sir.
Just take 2 minutes and then I will discuss this. Okay. Okay, so let us discuss this question.
Yes, sir.
Okay, so first option saying P W1 plus PW2 is a projection from V2 W1 plus W2, then this is 0. So when we get this thing, let me take the screenshot of this. So when we get this condition of first option, which we have to check whether this is 0. we have to take the composition, right? So we have only one thing, so we'll take this composition. Okay, w1 plus w2 composition with itself. But we know if it is a projection, then projection transformation. So if suppose this is the point, we are projecting this point here. Okay, and so this is some other vector space. Okay, so we are taking one vector and we are projecting on some other. Okay, and that we are calling pw. Then we got this point. Now if we take this point and again project on this vector space, what would be the same point, right? Is it clear
Yes, sir.
what I'm saying? Yeah. So that
Yes.
means this projection is equals to pw1 plus pw2. Okay, this one. Okay, basically we are projecting the same on so this would be equal to this we actually already know. Now if we calculate, then pw1 of pw1. Okay, um, so so pw of on pw. Okay, then pw on pw2 of pw2. Okay, I'm writing correct or not? First we take any vector on this, and then it will it will be divided on both, and then it will yeah. So this is correct. This is w2 on w2 plus p of w2 on w1. Okay, this one. So and these two terms are simply pw1 plus pw2. These two terms. Okay, and so which is equal to this. Then what about this term? These two terms. This term has to be zero, right?
Zero.
Together this would be zero. So yeah, this statement is true. Okay, and second statement, p square is equal to this p. Okay, is not a projection from v to w, but v2 w1 is a projection which is pw1, right? So this is equals to pw1. So that means this option is wrong because it is saying not a projection. Okay, anyone, any doubt? Any doubt in
Okay.
the question?
Yes. It's clear, sir.
Okay, uh, statement r is a matrix representation of pw. What is pw? Pw is the transformation or the projection uh, from v to w2. Okay, so v and w2 is a subspace of v. Okay, so this is pw. So, we are getting the some matrix. Okay, for that, then this matrix cannot be symmetric. So what if this matrix is symmetric? What will happen then? If it is symmetric, then A transpose uh, is a matrix symmetric. That means A transpose would be equals to A, right? This is the definition of symmetric, right? Do you know this?
Yes.
Yes. So A transpose would be A. Okay, so if A is a matrix representation of PW, then A cannot be symmetric matrix. So suppose this is R2, this is V, and W1 is just x-axis, and W2 is y-axis. Okay, in that case, we can take this example, right? So in that case, if we it is talking about W2, okay, then so y-axis basically. If we project all the vectors of R2 on y-axis, then we'll get the vectors of this form, right? 0 1 times some alpha basically, okay. So this time, so then if we take the basis of R2, which is the standard basis, and then project, so 0 1, sorry, t of 1 0 would be 0 0, right? And t of 0 1 would be 0 1, right? You are getting what I'm then taking y-axis as this w2, okay. And then so transformation means p of w2 basically, because this is the projection. So when we make this transformation matrix, because these are standard bases, so directly these will form the columns, 0 0 0 1. So this would be the matrix for this pw, right? So is it symmetric? Yes. See, if you take the transpose is equal to, so it is saying it cannot be symmetric. So we have found the counter example. It means it can be symmetric. Okay. There should be another way as well to solve this. Okay. At this time, I'm not getting. So this is the one way. We have just got the counter example that it can be symmetric. Okay. So that means this option is also not true. This is also not true. This is true. And fourth option is, so any doubt in these three options? Anyone? Okay. So PW1 minus PW2 is a projection from V to W1 plus W2. Okay. So what is the projection from V to W1 plus W2? P of W1 plus P of W2. Right? It is given in the starting of the question, which is not. So this option is also not true. See this. If W1 and W2 uh, are the two subspaces, then W1 plus W2 is also a subspace. So if PW1 is one projection on this subspace W1, okay, and the second subspace W2, these are the projection. Then if we want to find the projection on W1 plus W2, then this would be sum of these two projections. Okay. Okay. So for now, just all of you solve these questions. Okay, I'm ending today's session here, and
Okay, sir.
yeah. So rest of you solve all these questions, and if you get any doubt, just post on the discourse. Okay, I'll answer there.
Yeah, sure, sir. Thank you, sir.
Okay, you all can leave now.
Okay, sir.
Sir, PDF
PDF for,
graded solution and practice
yeah,
solution.
yeah. I'm just telling in the group. Okay,
Okay.
don't worry. I'm just telling.
Okay. Thank you, sir.